Circuits and capacitors. Introduction. The purpose of this lab was to use an online circuit modeling software as well as what we know about conservation of energy to predict different attributes of circuits with capacitors and resistors placed throughout them. The predictions we made based off of conservation of energy, the node rule, the loop rule, and Ohm's law were not only correct, but the numerical values were equivalent to the theoretical values we calculated, with a potential difference of 0 volts. Conservation of energy, node and loop rules, and Ohm's law. The lab required using the conservation of energy and in turn the node and loop rules, as Kirchhoff's laws of current are integral to understanding and building circuits. Ohm's law was necessary for calculating the theoretical values of current at multiple points in the circuits created. For the observed experiment, the system itself under study is the circuits in question and the surroundings is everything else. We assumed potential difference should be 0 and proved it. Current should be equivalent going in and out, as well as charge and energy were conserved. The 222 circuit calculations and predictions. We calculated the current at both ammeters to be 0.02 amps, which was correct when the circuit was constructed in the online model provided. When an ammeter is reversed, it reads as negative 0.02 amps. Voltmeter break explanation. One of the circuit's ammeters was replaced by a voltmeter. The circuit itself was broken, therefore there is no current, which is why the ammeter reads 0 amps. As for the voltmeter, it reads the potential difference for 3 volts, as the voltage from both of the batteries is present on one side of the broken circuit, but not the other. Potential difference measurements. The potential differences for marked segments were AB 3 volts, BC 0 volts, CD negative 0.96 volts, DE 0 volts, EF negative 2.04 volts, FG 0 volts, GH 0 volts, HA 0 volts. The sum of them all together was 0 volts, verifying no potential difference for a closed circuit. Parallel resistor ammeter circuit calculations. When an ammeter was inserted parallel to the 100 ohm resistor, the current increases to 0.06 amps, as shown in the model, with the following values calculated for question 12. 12A, 0.96 volts divided by 0.02 amps gave 48 ohms. 2.04 volts divided by 0.02 amps was 102 ohms, and 0 volts divided by 0.02 amps was 0 ohms for both C and D. Light bulb circuit. Charging a 10 ohm circuit took 11.67 seconds and discharging it took 13.43 seconds. Charging a 20 ohm circuit took 17.91 seconds and discharging it took 25.43 seconds. With the battery connected to the circuit, the bulb starts out as very, very bright, then decreases in brightness as the battery becomes charged. With the battery disconnected from the circuit, the bulb starts off bright, then slowly decreases in brightness as the battery discharges. Line of best fit and RC predictions. The expected RC value was 6 seconds as 30 ohms multiplied by 0.2F, while the experimental value was 5.38 seconds, which was calculated from the line of best fit from our model, with the slope being equal to -1 divided by RC. Taking the negative reciprocal gave us 5.38 seconds. Sources of error. Due to using a computational model, there should be 0 sources of error, with the exception of if I incorrectly started or stopped the stopwatch or did so imprecisely for the RC circuit explanation. What if and what does it mean? What if you were doing this in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and what would happen to the circuits that you hooked it up to? If you did this lab with real circuit components, access the virtual link above and see if you can determine how to behave differently from the real ammeter you used. An actual ammeter wouldn't give the zero resistance ideal of the digital simulations. They would give a calculated current which should be lower than the one in the digital model. What if you were doing this lab in real life and used a real battery to charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict this capacitor to reach full charge? Would this prediction happen in real life? Explain. If this were to happen in the digital model, it should be instant, but if it was in real life, resistance in real life circuit components is not 0, so the capacitor would not be charged immediately. Thank you.